Hello, welcome to a new chapter. This time we're going to start with exercise 3, which says a particle of mass m can slide freely along a wire AB whose perpendicular distance to the origin O is h. The line OC rotates about the origin at a constant angular velocity theta dot equals omega. The position of the particle can be described in terms of the angle theta and the distance q to the point C. If the particle is subject to a gravitational force, and if the initial conditions are theta 0 equals q0 equals q dot 0 equals 0, show that the time dependence of the coordinate q is blah blah blah. Compute the Hamiltonian for the system and compare with the total energy. Is the total energy conserved? Well, the first thing we are going to do is to calculate the Lagrangian, and once done, building the Hamiltonian will be very easy because we will just have to do a Legendre transformation. So what we are going to do is to find the position of the particle, the r vector. I can get it as the sum from this plus this. Therefore, the position vector of the particle will be first this here, which is h cosine of theta comma sine of theta plus q, the distance between the point C and where the particle is, times a unitary vector. Let's see what that unit vector is. If we draw the vertical line here, this angle is theta, and this horizontal line and this vertical line have to do with sine and cosine. So we put sine theta here and minus cosine theta because it points downward. Good. For practicing new things, we're going to use the well-known vectors that you already know, namely the polar base. Remember that the polar coordinates tell us in what angle we are and the distance we are from the origin. In each point, you will have two vectors, ER and E theta. So, since this vector is radial, it will be cosine theta, sine theta. And this guy will be the derivative with respect to theta. I hope you remember that, and you can check that these two vectors are orthogonal. And E theta goes in the direction of growth of the angle. So then we can rewrite the vector r as h times ER minus q E theta. And on the other hand, taking into account that the derivative of E theta is minus cosine theta minus sine theta times theta dot equals minus ER theta dot, and the derivative is minus sine theta cosine theta theta dot, then ER dot equals theta dot E theta. Okay, now we're going to calculate the velocity. So we have the derivative of the first term times the second plus the first times the derivative of the second, and the same here. Okay, and before continuing, we are going to remember the constraints, which are basically that h is a constant and the angular velocity is also a constant. ER dot equals omega times E theta dot equals minus omega AR, and of course h dot equals 0. So the velocity equals 0. It will be h omega E theta minus q dot E theta minus q plus omega ER. Let's factor out equals q omega ER plus h omega minus q dot times E theta. So, taking into account that the polar base is orthogonal, then the square modulus is simply this guy square plus this guy square. That is h squared omega squared plus q dot square minus 2 times h omega q dot. So the kinetic energy will be equals m over 2 times this yellow expression, and the Lagrangian equals the kinetic energy minus the potential energy. Let's see. It will be mg and the y component, but the y component equals the y component of the r vector. So we have h sine theta minus q cosine theta. Okay, let's substitute. So the Lagrangian equals m over 2, the whole expression, minus the potential energy. Let's delete a little bit. And let's go to the Euler-Lagrange equation for the q coordinate. So let's first calculate the derivative with respect to q, and it will be m over 2 q omega square plus mg cosine theta. Let's delete both 2's. Okay, let's now calculate the derivative with respect to q dot equals m over 2 q dot minus 2h omega, and let's delete the 2's. Okay, so the time derivative with respect to time will be equals mq double dot minus 0. Okay, so therefore the Euler-Lagrange equation tells us mq dot dot equals this whole quantity, and that's it. This is the equation of motion. Let's divide by m. Let's put omega square here. Let's move this up a little bit. Let's substitute theta for omega t. Let's solve the homogeneous part of this differential equation. One possible solution will be e to the omega t, because q double dot equals omega square times the same exponential, namely omega square q. Another possible solution is the same but with a minus, and let's see, q double dot equals minus omega square times the same exponential, so we obtain the same result. Both are solutions. Then the general solution is a times the exponential plus b the negative exponential. But it's possible to express the same homogeneous solution as hyperbolic functions. Remember, hyperbolic cosine is e to the I plus e to the minus I over 2. Similar thing for hyperbolic sine. Multiply by 2. Let's sum. Let's delete the 2's. And if you subtract, then you obtain e to the minus a. If we substitute, then we obtain a times hyperbolic cosine omega t plus hyperbolic sine omega t plus b, and the same thing but with a minus. Or if we join a plus b cosine hyperbolic cosine omega t plus a minus b hyperbolic sine omega t, and let's define small a and small b, and that's it. This is the homogeneous solution. Let's find now the particular solution. And looking at this expression, then we can say that qp equals alpha constant times sine plus beta, another constant, times cosine omega t. If we derive twice, then you obtain minus alpha omega square sine omega t minus beta omega square cosine omega t. So if we factor out minus omega square, we obtain this. Let's substitute minus omega square times qp equals omega square qp plus g cosine omega t. Let's simplify a little bit. We can now write 2 omega square times q, that is alpha sine plus beta cosine. I have move this guy to the other side, plus g cosine, and all this has to be 0. So 2 omega square alpha sine plus 2 omega square beta plus g times z equals 0 implies that 2 omega square alpha equals 0 and 2 omega square beta plus g equals 0. So alpha equals 0 and beta is minus g over 2 omega squared. Okay, let's delete. The particular solution will be qp equals 0 plus beta, but beta is minus g over 2 omega squared cosine omega t. Therefore, the final solution is q equals qh plus qp equals a cos omega t plus b sin omega t minus g 2 omega squared times cosine omega t. We now impose the initial conditions, which are q at 0 equals q dot at 0 equals 0. If we substitute the first one, 0 equals cosine 0 times a plus b times 0 minus g 2 omega squared cosine 0. This is 0. It implies that a equals g over 2 omega squared. So substituting, we have g over 2 omega squared times hyperbolic cosine omega t minus cosine omega t, and that's it. Okay, let's now compute the Hamiltonian. Let's put this to one side because the only thing we need is the Lagrangian. Okay, let's compute first of all the canonical momentum, that is P, and as you know, the definition is partial derivative of L with respect to Q dot. We already have it. It was mq dot minus mh omega. From here we can isolate Q dot, which is P plus mh omega divided by m equals P over m plus h omega. Okay, the Hamiltonian, as you know, is equal to P times Q dot, if we are in one dimension, minus the Lagrangian. So P Q dot P over m plus h omega minus all this, m over 2, q square omega square, h square omega square plus q dot square, but we know what q dot is, square, minus 2h omega, and also q dot, but q dot is p over m plus h omega. And now minus, so plus m g h sine theta, but theta is omega t, and minus plus, so minus mg q cosine theta. So we are going to expand this expression. It will be q square omega square plus h square omega square plus p square over m square plus h square omega square plus 2h omega over m p minus 2h omega over m p minus 2h h square omega square. Let's see. 1 minus 2 is minus 1, and we can delete this. This is positive and this is negative, so we cancel them out. Okay, and finally this term with this term cancels out as well, and the remaining terms are very simple. So the Hamiltonian will be this expression p square over m plus ph omega minus m over 2 times the yellow expression q squared omega squared plus p squared over m squared, okay, plus the remaining terms, plus mgh sine omega t minus mgq cosine theta. So the Hamiltonian is, let's see, p squared over m minus this term. It gives us minus p squared over 2m, then 1 minus a half, then we have a half. So we can delete it, and this is the final Hamiltonian. Let me substitute omega t. So, very good. Let's see, compare with the total energy. Is the total energy conserved? Let's see. What is the definition of energy? Remember, energy equals the kinetic energy plus the potential energy. Then it should be all this plus the potential energy. That the potential energy is this expression, but with the opposite sign. Let me put omega t here, and also in here, and in here. Okay, in order to compare the energy with a Hamiltonian, we need to substitute q dot as a function of p. But as we know, q dot is this expression, and minus 2h omega q dot. But q dot is also p over m plus h omega. Let's expand this expression. P squared over m squared plus h squared omega squared plus 2p over m h omega minus 2h omega. Let's delete p m minus 2h omega h squared omega squared. Both these terms vanish, and 1 minus 2 equals minus 1 minus h squared omega squared. The q dot part of the yellow expression is this with a plus. So the energy will be, let's see, m over 2 q squared omega squared plus m over 2 h squared omega squared plus p squared over 2m minus m h squared omega squared over 2 mgh sine omega t minus mgq cos omega t. And looking at this term, we see m over 2h squared omega squared, and the same thing but with the opposite sign. So we cancel them out. What else? I think we're done. Let's put this guy to the left and this guy to the right for aesthetic reasons. And this is the energy. If we compare, this term equals this term, okay? But this term has a plus sign and this term has a minus sign. And this term is missing and these two terms agree, okay? But with these two problems, H and E are not equal. So the Hamiltonian is not the energy in this case, in this exercise. Okay, now we're going to try to relate all this with what Santi told you in the theory class. If you remember, Santi stated a theorem that says as follows. If L has the shape T, T2 plus T1 plus T0 minus V2 minus V1 minus V0, where the 2, 1, 0, etc. reminds us the dependence on Q dot square, Q dot to the power of 1 or to the power of 0. So the theorem states that if L has this shape, then the Hamiltonian will be, for sure, T2 minus V2 minus T0 plus V0. But on the other hand, the energy equals T2 plus T1 plus T0 plus V2 plus V1 plus V0. So in order for these two things to coincide, we need V2 equals 0, but also V1, T0, and T1. If we look at the Lagrangian, T2 is equal to, let's see, m over 2 q dot square. T1 is equal to m over 2 minus 2h omega q dot, and T0 equals m over 2 q square omega square plus h square omega square. So T1 is different from 0 and also T0. Therefore, the conditions are not met, so the energy cannot be the Hamiltonian. And remember that there is another way to approach this problem. The problem can be reduced to two conditions. The first condition, remember, it was the vector r doesn't depend on t explicitly. And the second point is that the potential doesn't depend on velocities. If there is no dependence on t and velocities in the potential energy, then the Hamiltonian equals the energy. But if you remember, at the beginning of this video, remember r equals h cosine omega t sine omega t plus q sine omega t minus cosine omega t. There is an explicit dependence on time. So we could have already suspect that the energy and the Hamiltonian were not going to be the same at the very beginning. And the final question is the energy conserved? Okay, to check this question, you can express the energy as a function of t, because we know the solution of the equation of motion, and if you substitute p for what is, and substitute what we have found at the beginning of this video. Remember, q equals g over 2 omega squared times hyperbolic cosine omega t minus cosine omega t. If you do this at home, the total time derivative of the energy, you will see that it's different from 0. So the energy is not conserved. Okay, now let's do exercise 4, which says that a particle of mass m moves in one dimension under the influence of a force, this force, where k and tau are positive constants. Compute the Lagrangian and Hamiltonian functions, compare the Hamiltonian and the total energy, and discuss the conservation of energy for the system. Okay, what we know is that if the force is whatever, k over x squared times e to the minus t over tau, what we know from this is that the potential energy is minus the integral of this force. We are in one dimension. So since k is a constant and t over tau is like a constant if we consider as a part of the integrand of this integral, then they can go out from the integral, and we have, so the potential energy will be minus k e to the minus t over tau x to the minus 1 divided by minus 1, and we should add a constant, let me call it a. This minus with this minus cancel out, the one also, and let me put x in here. And now we're going to investigate what is the value for a. We can establish that thinking about boundary conditions. So let's imagine that it's normal for us to think that when x is plus minus infinity, then the force tends to 0. Then if we substitute x for infinity plus minus infinity, this term gives us 0. If we want the potential energy to be 0 in the infinity, suppose we are happy with this, then this condition implies that A must be 0. Okay, so we have now the potential energy that is K over X e to the minus T over tau. Great. Now the Lagrangian will be m over 2 x dot squared minus the potential energy. Perfect. Let's compute the Hamiltonian. So we need the canonical momentum that, as you know, is defined by partial derivative of L with respect to q dot, in this case x dot, coordinate, and this is m x dot. So the Hamiltonian will be p q dot minus L, namely, if we substitute, in this case q is x. So x dot equals p over m, so we have p over m minus L, m over 2 times x dot squared, but x dot is p over m squared minus k over x e to the minus t over tau. So this is p squared over m, and this is minus a half p squared over m. So 1 minus a half, this is equal to a half p squared over 2, over m. So the Hamiltonian will be p squared over 2m minus this. Oops, sorry, this must be a plus sign. Sorry, because of this minus, with this minus is plus. Sorry. So we have the Lagrangian, we'll put it here. Let's move the Hamiltonian to this position. Okay, compare the Hamiltonian and the total energy. Well, as we have seen before, we know that the Hamiltonian has to be T2 minus B2 minus T0 plus B0. But looking at this expression, the whole expression, we see that T2 equals m over 2x dot squared, B2 equals 0, T0 equals 0, and what else? T2 and B0 equals k over x e to the minus t over tau. Then the theorem says that the Hamiltonian has to be T2, this expression, m over 2x dot squared, minus B2, and 0, minus T0, 0 also, plus B0, plus k over x e to the minus t over tau. Well, this must be expressed with a p variable, p squared over 2m. Okay, that's correct. And the other thing is that the energy must be, as we mentioned a few minutes ago, it has to be T2 plus T1 plus T0 plus B2 plus B1 plus B0. We know from here that B2 and and T0 are 0. T1 is 0, looking at this, because there is no dependence on x dot in the kinetic energy, so this is 0. And B1 is the same, because the potential energy doesn't depend on velocities, so this is 0. So the energy must be T2 plus B0, and it coincides with the Hamiltonian. So it is equal to the Hamiltonian in this exercise. Remember, we have dH dt equals minus partial L with respect to t, and as the Lagrangian depends explicitly on time, then this is different from 0, and then h is not a constant. Since h and e are equal, then e is not a constant. So that's it. Thank you very much for watching this video and see you soon.